So a quick little diversion about the power cables that came with this unit. Again, you can get these for maybe 60 bucks off of eBay, plus shipping, and off the shelf they're designed to handle, you know, military battery standards, but maybe there's a way you can hack the unit to charge other types of batteries. So I figure, why not take the chance? But then I just have to marvel at the quality of the cables that they give, and at the same time some of the cheaping out that just seems a little silly. This is the shore power AC cable, 5-pin connector, just like the vehicle power cable. The connector itself is like an Amphenol or other high quality. No, this is an ITT Canon connector. It's hard to see from this far out zoom on the camera, but it's an ITT Canon connector. So this connector is probably 60 to 100 bucks US, just to get this connector. They use good quality SJ service junior grade cord, 16 gauge, 60 degrees C rated cord, 16 gauge 3 conductor for live, neutral, and ground. The heat shrunk part number on it, so if you have to replace it, you can do so. And they didn't cheap out on the length of cable either. So you think, they went to all this expense, but they use an overmolded NEMA 515 plug on the end. All it takes is for one idiot to trip over this cord, and they've damaged this cable. And if you don't have a field replacement, where you can just snip this off and, you know, screw on a new connector, you're kind of SOL. So that seems like a bit of a, not an oversight, but just like, you're already spending probably thousands of dollars on this unit. What's another $30 high quality, you know, Hubble connector on the end? So that's the AC power cord. This is the DC vehicle power cord. It's service outdoor oil wet SOOW rated cord, 90C down to minus 40C. So this is obviously much more severe environment. Same ITT Canon connector on the business end, very clearly labeled plus and minus. And this neat little thing about the way they did this heat shrink boot. You know, it's like, okay, they've got these two wings and they fed the cable through and they heat shrunk it. And then I just have to marvel at the simplicity of it. You can do this in the field. Somehow you heat it up and you just crimp it with pliers. This is literally a plier crimp mark. So I'm gonna have to figure out, maybe you like heat this up with a blowtorch and then you pinch this shut. Yeah, quick little diversion on the cables. Back to the main video. Alright, so we've got the, what looks like the charge control board under the camera. All of the power transistors are on the outer rim, and they appear to go into a heat-sinking transfer plate. Not even a transfer plate, a bracket. So each of these clips clamps the transistor or power device across a insulating sill pad sheet, and it goes onto this metal bracket. This metal bracket goes straight to the heatsink. It looks like it's actually either been brazed into place or welded, because it looks like it's a discrete part. And there's an identical one on the top edge here. So without the special tool to release these brackets, I'd have to basically use a pair of screwdrivers to pull the tabs out, and that looks like a lot of effort. So I don't think I'm going to unmount this board. I was going to, but I've changed my mind. Alright, we've got some very large Renco inductors. These are very beefy inductors. We've got some smaller inductors up here, some power resistors, and what looks like a power connector. We've got another power connector here. These go to the resistors. So these are for the resistors. This is where your main DC power input goes. So this connector is going to be transferring power up to the controller board. Now we've got, I recognize these already, AD8483. These are, I think, 4-channel digital potentiometers. They're SPI devices. So these are 4-channel digital pots. Presumably they're going to be used to adjust the set points of voltages or something. We've got the control signal here. That's a 10-pin, not an 8-pin. My bad. So we've got that. We've got, interestingly, we've got a what looks to be a fan out of connections here, and there's a test point or a jumper here. But I'm really curious what chip this is. Oh, it's a 7.4 AC 138M. It's kind of curious. It's interesting. Got a couple signal lines from the multiplexer going up, snaking off into the main board. Alright, so it looks like we've got two small transistors backing up these two international rectifier IRL 3705N MOSFETs, 55 volts, 89 amps, and given the proximity, I would not be surprised if these two MOSFETs connect to the power transistors. If they're putting two small transistors in front of these two, maybe it's a current limiting function, but that seems a little strange because if these are in linear mode, they would dissipate a ton of heat. Okay, so one of these pins is common with positive, which then goes through the resistor, back out into the drain of the MOSFET, and then to wherever it's sinking power into. That's very strange because this is an N-channel MOSFET. Alright, and I can't figure out where this other one goes, but okay. So these are in some sort of current limiting function of some sort. Let's take a look at the rest of this real quick. Got a whole bunch of capacitors. They look like Mallory capacitors before Cornell AA and Mallory merged, I think, because I recognize that old logo. It's a funky looking M. So they didn't spare any expense on the capacitors, that's for sure. The current transformers are all made in China, and they've got just one loop of not even nylon coated wire through them. Interesting. I'd really like to find out what transceiver chip is in proximity of this, but maybe there isn't a transceiver. Maybe it really is, well, no, it has to be some kind of digital mode because these are SPI. That is an op-amp. It's a bunch of diodes. Power transistors. This is going to be a buck converter of some sort, it looks like. There's a couple 5-pin components here as well. Very curious. I wish I could get at these. There's a bunch of power electronics. 220 microhenry inductor here. And they even mark the inductance on these devices so that if you really needed to, you could test them. It's really cool stuff. Okay, so let's look here. We've got what look to be two resistor arrays combined with a bunch of capacitors. So that's very interesting. You've got a whole bunch of capacitors in series with the resistors. Now, why would that be? Because normally if you were just trying to do voltage dividing and sensing, these would just be in a direct arrangement. And if these were all capacitors for decoupling, you would expect that these decoupling capacitors would all share one common rail. Instead, they appear to be a resistor capacitor arrangement to what looks like some sort of a voltage sense bus. It's very strange. I can't figure out what this connector is for. Yeah, I don't know if I'm going to get too far with this one. This is a very complex and befuddlesome design. Got a nice little tantalum capacitor up here too. Another tantalum there. A bunch of electrolytics, a couple power resistors, lots of film caps sprinkled around to act as very low ESR, low inductance capacitors to absorb any ripple current. smooth everything out. Yeah, I think that is as far as I'm going to get with this stage of the teardown. Okay, so for now, I think I'm going to end it here. If you like the video, like, subscribe, comment. Let me know in the comments if you've ever dealt with a unit like this before, and if you know what any of this is. I mean, not this specific board, but how the whole unit talks to itself and communicates across the entire unit.